there's a bit more to discuss after what Tom's will talk about, but at least it will give you a good overview. So the upstreaming process started like back in 2019, 20, approximately, back to when initially DPC++ started to appear. At this time, basic Clang changes were added upstream. The device and host compilation mode were added at this moment. Even if it doesn't do much, this flag is still there for the basic support. A few attributes. There was some address space support that were added as well, plus a bunch of bug fixes that were highlighted by those prior changes. But everything was put on hold after a few difficulties to upstream the few initial the components. Took way more times and then required heavy discussions with some members of the community at the time. Fast forwarding in 2023, the whole process was kickstarted again. This started with a series of requests for comments to cover the various aspects of the tooling. Sorry. So the tool are matured, and so therefore several RFC were put forward. One to cover the client frontends, one to cover the client drivers. So the drivers, the component that orchestrates and schedules all the calls to the compiler tools in order to produce your applications. All the new LLVM passes and tooling that would support the SQL compilations, and one for the runtimes. Everything was put together into that RFC here that just sums up all the changes that was requested, suggested community, as well as linked to the individual RFC that I mentioned before. So that was in more than a year ago now. Progress has been there, maybe a bit slower than one would have wished for, but still progress has been made. The front end is by far the component that required the most changes and rewriting, and that's what Tom is going to present just after that. Right now, we have the handling of new SQL kernel entry points attributes, as well as a new process being added into this, plus some other new diagnostics. So that's now upstream. There's much more to come. The driver has now an initial driver support for orchestrating the host and the device compilations, as well as linking all the parts. A new tool is added to support the linking step as well, following a new design of the offloading module. Tooling is being on tooling side. The module splitting is being added as we speak. There's a pending PR for this, and the runtime has two components. One which is UR and requires integrations with liboffload, and that's being an ongoing process for the past year. It's a bit slow, but the progress is being made, and in same times, the SQL runtime in itself is being prepared to actually being upstreams with as a temporary solutions using UR directly as an external component. All right. Is there any questions about all of this?
I guess, Victor, just to reiterate on what you're saying, it is the upstream of SQL is very important for UXL Foundation, because that what basically means is that we can have an independent implementation of SQL up there in LLVM upstream, and it's a place where many people can contribute, and there is many components that we can reuse. So it's good that we have discussions about that, but also I will encourage people on this call to talk to their companies and the people that they're working with, to go to the RFCs, to participate in LLVM upstreaming and support the efforts that we are we're doing to get SQL upstreaming, because that's what we need, the community supporting what we're doing, giving feedback on the pull request, and showing that there is interest in having SQL as a programming model enabled in the client compiler. Any thought questions before we keep going?
Maybe you cover it in the next parts, but what parts of the UR are getting upstreamed? Is it for all the GPU backends or only for Intel? Or only the backend agnostic parts and the backend specific parts will be outside?
So, so basically, the Intel part will be upstream to libfloat. There is already some support for NVIDIA and AMD. But that being said, so Intel requires a new component, what more I meant. Otherwise, for this other target is already there. The libos offload API is currently doesn't expose all the features that SQL would require. So we are working with the community in order to expand the API in order to support everything. And that will see also the additions of components from the major vendors that we have right now.
Okay.
So do you say that the unified runtime will be merged into the liboffload? That's what you say?
That's the plan.
That's the plan, yes. I don't know if merge is the right term, but it's definitely the plan is to have a single runtime layer. Yeah. Questions, comments? Should we hand over to Tom now?
Yeah. All right. So handing over to Tom. So since the client Intel architect is also representative for the C++ standards and has been working for quite some time now on to helping improve the support of SQL in VP++ and now upstream LVM. All right.
All right, thank you very much. I'm trying to get my screen configured here. Are you able to see slides okay? Or am I covering them up?
We can see a slide with a front page, I guess.
Okay, I have the Zoom participants in chat open up as well. I'm not sure if that's gonna block something. So just let me know if part of the screen is obscured. So thank you everyone for joining us today. I intend this to be very informal, so please ask questions as we go. You can use the raise hands feature under the React button, and I will try to keep a lookout for that if Zoom plays nicely with me. Okay, so I'm going to start by talking about SIG kind of at the high level and what the front end responsibilities are. As I'm sure you're all aware, the SQL specification was intended to support many different kinds of implementations, from a single library implementation that doesn't actually require any additional assistance from the compiler to implementations like DPC++ and what we're upstreaming to Clang that support more complicated types of compilation. In fact, I'm going to switch briefly to a diagram that Victor provided me earlier today that shows kind of the compilation workflow that happens with the DPC++ compiler. What we are going to be upstreaming to Clang does not do all the things that we see here. So we'll kind of talk through that a little bit. But the basic workflow is that you have a SQL source file, a compiler driver typed in, and then it does a multiple compilation pass. So it'll compile the source code once, targeting the host compiler, and then it will compile it again for each device that is being targeted at compile time. From there, the compilation output goes through different paths. For the host compilation, we just get an object file that's going to get linked in for the final binary. For the device compilations, it's much more complicated. We get LLVM IR out. It goes through different linking phases, targeting different backends such as SpearV, but could be CUDA or OpenCL, things like that. And then all of those different device objects end up getting linked together into a wide binary that has all of the object files needed for all of the supported devices. Hopefully that makes sense. Hopefully it's something most of you are familiar with. So I'll jump back to the slides. So for an implementation that is similar to the DPC++ one, where we're going to have integration between the SYCL runtime and the SYCL compiler, there are a number of responsibilities that the SYCL front end ends up with, or the compiler front end. The main ones are that it has to recognize calls to SYCL kernel invocation functions so that it can emit SYCL kernel entry point functions that are the entry point on the device side for initiating computation or control flow on a device. And in doing that, once it's identified a SYCL kernel, then it has to identify all of the functions that are reachable from that SYCL kernel that might be called. And those have to be identified so that the compiler can then emit all of those functions for each device. So the goal is not to emit everything that's in the SYCL source file for each device, but just those things that are relevant for a device execution. In order to actually get code to run on a device, integration is required with the SYCL runtime to arrange for those calls to the SYCL kernel invocation functions to pass arguments from the host to the kernel executing on the device. So that might be copying memory across device memory boundaries or making it somehow accessible to a device. The front end doesn't know anything about those kinds of details, but it does need to know some of the protocol and have a protocol with the SYCL runtime library to coordinate some things. And we'll go into that a little bit more later. And then finally, one of the main responsibilities is diagnostics. The SYCL specification is, like I said, designed for multiple implementations, and that puts certain restrictions on what is considered a portable SYCL source file. So when SYCL kernels are given names, there are requirements about the type that is used as the kernel name. You might see it in the SYCL spec referring to forward declaration requirements. There are restrictions on what types can be used as parameters for SYCL kernels. So we have to diagnose those and make sure that we don't emit code that would require an argument passing method that the SYCL runtime can't support. And then SYCL places lots of restrictions on what language features can be used in device functions. So we need to be able to identify those and let the user know if they're trying to do something that's not allowed.
Hey, Tom, would you mind switching to presentation mode?
Oh, I'm sorry.
That's fine. Thank you.
Yeah. Okay, so the DP C++ implementation strategy has, like I said, a multiple pass compilation model, one pass for the host compilation, one pass for each device compilation. And then it uses integration headers and footers to coordinate between the host and device compilation. And part of the goal of integration headers, or perhaps the main goal, is to enable a compiler that is not SYCL aware to be used as the host compiler. So something like GCC or MSVC. However, in order to actually do the compilation on the host side, there needs to be some information provided about the SYCL kernels for the SYCL library to use. But the host compiler can't provide that. So what happens is that during device compilation, source files are generated by a SYCL-aware device compiler and the information is put into header files that are then pre-included when compiling for the host. And this makes certain declarations available for the SYCL runtime library to reference so that it knows, or it can be aware of SYCL kernels and their various properties. For example, the function names, how many parameters they are, what kind of parameters they are, source location information for diagnostic purposes. And then SYCL has these specialization constants, which maybe we'll talk a little bit more about later. We don't have, we haven't made much progress in really looking at those at this point. So when we started to engage with the Clang community for upstreaming the front end side, there was considerable objection to some aspects of the DPC++ implementation. And so compromises had to be made for, to the design to address those complaints and make the implementation something that the community was willing to have be part of the Clang distribution. So one of the top complaints was that they did not like the integration header and footer approach, and for good reasons. The limitations that are placed on SYCL source files to support the integration header and footer approach make for rather unintuitive restrictions. And by using a SYCL-aware host compiler, a lot of those restrictions can just be completely avoided. So it makes the programming environment more intuitive, more natural for anyone that knows C++. So the upstreaming effort then is going to require that the host compiler be SYCL-aware, and in this case, that basically means the host compiler will be Clang, and that there will be no support for use of a third-party host compiler such as MSVC or GCC to be used at all. Now that's something that we can look at enabling in the future if there is sufficient demand. We can approach the community once we have a working implementation with Clang with a SYCL-aware host compiler and see if there is enough demand for supporting these other host compilers. So that's a fight for another day if anyone wants to see that happen. Additionally, there was considerable discussion about the multiple pass compilation model. Some of the Clang community really wanted to see a one-pass compilation model, and that would be, but what we mean by a one-pass compilation model is that the source code would only go through the front end once, an AST would be produced, and then a code generation pass would be done multiple times, once for the host and once for each device off of the AST. That has some very attractive properties to it, but is also technically challenging to implement. And parts of the SYCL specification don't really work real well in such a one-pass model in terms of macros and use of system headers and things like that. You can imagine for different devices that you have different architectures, that things like numeric limits can be different in some types, or in some cases. So we were not inclined to pursue a one-pass compilation model, but we did get agreement from the community that a multiple pass compilation model is okay, so long as we don't restrict or place unnecessary impediments in front of support for a future one-pass compilation model. And then finally, the other compromise was they wanted changes to how some of the SYCL information is represented in the Clang AST. And I'll show an example of that in one of the next slides. But first, this is an example of what DPC++ implements today in terms of the front end integration and coordination with a SYCL runtime. So the SYCL runtime would declare a function like this SYCL kernel entry point 1. it'll be a function template that takes a kernel name type as its first template argument, and then the type of the kernel itself, typically a lambda, otherwise a class functor, as the second template argument. And an attribute, the SYCL kernel attribute, is what nominates this function as a special function that effectively represents the offload kernel or the SYCL kernel entry point that will be emitted on the device side to initiate execution of a SYCL kernel, the SYCL kernel being the lambda or class object. Within the body of the function are the instructions that need to happen on the device side to kick off that execution. And in this case, it's just calling the kernel directly. But note that the body of the function is conditionally included only for device compilation, with the result that a call to this function in host code is going to do nothing. And that's intentional. That's the design is such that an ODR use of this function within the host code suffices for the entry point to be emitted on the device side. But when that call is actually made on the host code, we don't actually want it to do anything, right? That's the call is not necessarily made at a time where we actually want to kick off the execution. That's the job of the SYCL runtime to do any scheduling required for that. So on the host side, it becomes a no-op. So the SYCL kernel attribute had some deficiencies that were not exactly what we were looking for. And so to address those, we are introducing a new attribute called SYCL kernel entry point. It differs from the SYCL kernel attribute in that it takes the kernel name type as a direct argument. So in the DPC++, the compiler has to guess or to just assume that the kernel name type is the first template argument, and therefore it requires that this entry point function actually be a function template. So we're relaxing those constraints by allowing the SYCL kernel entry point attribute to be used with non-template functions, and to allow the kernel name type to be a parameter or an argument. So it can come from a template argument, it can come from another type at namespace scope or anything like that. Since we are going to have a SYCL aware host compiler, we don't need to we don't need to adhere to some of the restrictions that the SYCL specification allows for. For example, in DPC++, it used to be that you had to provide an additional command line argument to enable support for unnamed lambda kernels. And that had to do with difficulties coordinating names of otherwise unnamed lambdas across the host and device compilation. Eventually, a solution was worked out in DPC++ that works fine when DPC++ is the host compiler, but things like unnamed lambda kernels are not supported by DPC++ when using a GCC or MSVC host compiler. We don't need to worry about those restrictions for Clang, so we'll just have full feature support is the intention. As I mentioned, there's AST changes involved. We'll go through those shortly. We're also changing the names that are generated for the SYCL kernel entry point function, which we often call the SYCL kernel caller function as well. With DPC++, it uses arguably an abuse of the Itanium name mangling scheme. It uses the name that is generated for the type info of a type, and then takes that name to use as the name of the generated kernel entry point or the offload kernel. And that results in a name that is not very meaningful. It gives you the name of the kernel name type, but it doesn't actually do anything to otherwise indicate that this function is an entry point function. So we came up with a new naming scheme that will be used for that, and one that will work properly with some of the tools you might use to look at demangled names. And then finally, because Clang is not going to support integration headers, we needed a new mechanism for the host and device compilation to coordinate those SYCL kernel properties. And so built-in functions are what we intend to use to provide that. So that during host compilation, where we have a SYCL-aware compiler and we can see the SYCL kernel functions, we can just use built-in functions to enumerate like the number of kernel parameters and their kind and such, and then make that available to the SYCL runtime. Again, I hope I'm making sense with all this, but please feel free to interrupt me with any questions. So here's just a summary of the changes that we're looking at between the SYCL kernel attribute and the SYCL kernel entry point attribute. I already went through these to some degree. The point I'll note that from this slide is that the new attribute does not require that conditional if-def for device compilation only. Instead, this will implicitly have the body of that function be a no-op when compiled for host compilation. So SYCL runtime authors can just write these functions, write the device code directly in the function itself, and when a call is made to that function from the host side, it just has no effect other than to trigger emit of the offload kernel, the entry point function for device compilation. So the AST changes, I'll go show on Compiler Explorer what DPC++ does today. And this might be too small, but hopefully you can see it well enough. So for the source code, we have a use of the SYCL kernel attribute defining an entry point. We're kind of, what we're looking at here is what would be low-level implementation detail deep within a SYCL runtime library. And most of that's not shown. This is just the function that gets us at that low-level coordination with the front end. And then we have an example kernel that has 2 data members. And down in main here, we're just constructing that kernel object. And then we're calling this function, giving it a kernel name of class K and passing the object to it. So this call is what suffices for the entry point function to be emitted during the device compilation. Now, on the left compiler pane here, we have the host compiler compilation, and on the right is the device side. And scrolling down on the device side here, whoops, get these out of the way. Sorry, messing up my workspace. And I lost my share window. What did I do?
Can I still see your browser there, Tom?
Do you? Okay, good.
We see
Something went wrong.
Explorer and the two outputs there.
Okay, I think I'm actually seeing the Zoom window now is my issue.
Yeah, the Zoom
Okay.
the Zoom window is invisible for the people watching. Yeah.
Yeah. Okay, here we go. Now I can see it better. So this function that we see here, this is what DPC++ throws into the AST for that entry point function. And you can see here the name that it gives it, which, as I said before, is the Itanium mangling for the type info data for this K class, right? So this is, the objection here is that typically in the AST, things like name mangling are a lower level concern. Right? If we go back and look at other functions, they are not, we don't see mangled versions of their names, like for the cyclokernel entry point, right? So that right away stands out as, we're leaking some implementation detail where it doesn't belong. And so we're trying to avoid that, but also this function just kind of appears here. It's not referenced from anything else within the AST here. It's sort of just this isolated function that that's difficult to tie back to the source code in any real way. It does show some of the detail in what the front end has to do as part of initiating a cyclokernel execution. What we see is that this function takes 2 arguments, and these correspond to the data members of the kernel object itself. So what happens is during the kernel call, the kernel object gets decomposed into its data members. Those get passed individually to the function. And then we see that the function as generated by the front end reconstitutes or reconstructs the original kernel object. So it declares a kernel object here and initializes it with those 2 data member arguments. And then from there, it executes, or it has the rest of the function body, which in this case was just this call to the kernel function, the function call operator. So you can think about it when the device execution is initiated, this is the function that's first called. It puts together the cyclokernel object, performs the call, and then we're back into user code, or into the normal, what the user wrote in the body of their cyclokernel function object. I can switch back to the presentation. So since that was kind of those 2 concerns of the name leaking out and the function that's just kind of detached from the rest of the AST. To address those concerns, what we did is we introduced 2 new AST nodes. So an outlined function decal is going to have the details of the entry point function, such as the number of parameters and the generated body for it. And then there's a cyclokernel call statement, which is going to appear or get inserted in the body of the cyclokernel entry point attributed function. And that will wrap the original body and contain the outline function decal with the transformed body, as we saw. So we've now had enough PRs land upstream that we can demonstrate this on Compiler Explorer. So if I go over here is effectively the same program. The kernel entry point function has been rewritten to use the entry point attribute with the kernel name type named from the template argument. And if we go into the AST, we can see here's the function decal for the generated entry point function. Over here, we can see it's got the template arguments. And then for the body of it, the cyclokernel call statement appears here with the original code for the function body. So just this call to kernel appearing here. And then the outline function decal, which has this implicit, it'll have a sequence of implicit param decals that correspond to the arguments given here. Now in this case, we're passing the kernel object as just a single object, whereas in the code I showed before, the kernel object was broken down into its constituent members. We are trying to reduce the amount of that deconstruction that we do with what we upstream. We're still going to have to do it for support of SYCL special types and such. But in this case, our kernel object, doesn't have any kind of SYCL special types like streams or accessors and such. And so we really don't need to break it down. And so we're going to save some processing time by not doing that. And then we don't have to reconstruct the kernel object itself. We can just do we can just call it directly. And what this demonstrates is basically a replacement for the need for the integration header and footer that we talked about earlier. This same AST is generated for both the host and the device. And that's essentially our requirement for the coordination between them. Each side gets to see the same detail about the salient properties of the kernel itself. So the number of parameters, the kernel name type, all of that. And then those built-in functions that will take the place of the integration header to coordinate with the runtime library will operate based off of this data. Okay, any questions on that?
I'm curious about whether this is implemented in a full working SYCL compiler, such as DPC++, or is just something aside that you're pushing and without testing the big picture?
Excellent question. Yeah, so we did do a proof of concept within DPC++ before pushing this all upstream. So we had implemented the AST support and some very minimal code generation support. And then I forget who did the work. Somebody did the work to the SYCL runtime to use built-in functions to do the coordination. And we've implemented enough support of those built-in functions to be able to do a proof of concept, basically. And so, yes, we were able to get a very, very simple hello world to execute with that. But it's very limited. All we could do was pass in basic data types, and that's about it. So more will be coming. Any other questions?
Yes, hi, I have a question. So if you go back to the previous slide where you have the example, or actually the browser, sorry.
Oh, okay.
Right, so I have a question regarding the accessor here. Does it mean that I can use on the host side an instance of K and access directly DM1 and DM2 after the kernel is launched? So it's host accessible? And is this data device only? How this operates under the hood? Or it's not specified, you can have a...
Yeah, good question. So basically, yes, you can, because this kernel object, it's just a C++ class and an object, right? And here it's constructed. I didn't do any initialization, so these have indeterminate values in this case. But if it had been initialized, send it to the entry point function, it gets copied to the device operates on it. Now afterwards, so if I were to come in here and do something with one of these values.
Exactly, yeah.
Yes, so I can. However, if that value was modified on the device side, we don't copy that result back. So all you'll see is what was there on.
So it should be a call to wait for the kernel to launch, right?
Oh, there would be, yes. Here I'm at you consider this the very low level details of inside the runtime library. Like I haven't implemented the SYCL handler here with the single task or parallel for or anything like that, right? That would all be built on top of all of this. And that's where that synchronization comes into place too.
And inside the so whatever is declared inside the kernel, that means device memory, or could be share, like type of share memory in oneAPI.
I don't. Maybe Victor probably knows this better than I do. My impression is that whatever's in here is going to get copied to the device. So you get a separate copy. I guess it's going to be local device memory, and not shared. If you're going to do shared memory, you can put pointers to globals in here. If you have if your device supports USM, right, unified shared memory, then you can use those pointers. If your device doesn't, then I think you have to use the SIGL buffers and
Yeah.
such.
Yeah, that's correct. Yeah, what you say is correct. All of the so DM2 and DM1, they will be parameters to the kernel. So in OpenCL terms, it will just be private memory.
There are no changes to the underlying memory model.
Sorry, so
in
you
this
say private
front-end
memory
rewrite.
or global memory? Oh, global memory to the device, I mean. What do you mean private? Like private registers?
Which language are you talking about? OpenCL? CUDA?
OpenCL, mapping to OpenCL, yeah.
So
I think it's actually indeterminate because, I think you can't observe it because the operator call is const, so you can't write to them anyway. So they're just constants.
Right.
I forget, do we actually require it to be const?
Yes.
yeah.
Okay.
It looks like a very nice feature. Can you nest it, things like that? Like use structs and destructs and then compose?
Yes. Yeah, because the typical use case, right, is that your kernel object is a lambda.
Yeah.
So instead of doing this, I might capture K, and then do an invocation on it, something like this, right?
That's cool.
Yeah.
All right, thanks. That's all for me.
Okay. Okay, so this is what we just showed in the compiler explorer. And maybe this is a little bit clearer about the AST, or you can see it a little nicer. Again, we have the kernel entry point function, SIGL kernel call statement inserted by the compiler around the original function body, the outline function decal. In this case, I'm showing that an example where the kernel object was decomposed into its constituent members. So we see DM1 and DM2 as implicit parameters, and then showing how that's reconstructed to create the kernel object initialized with those data members, and then a call to this variable to do the work of the SIGL kernel. This transformation, in case it's not clear, if we go back and look at the code here, from an AST perspective, we're referencing a function parameter here, the kernel parameter, and then calling its function call operator, right? So the function call is happening based on the parameter. However, in the transformed AST, that call doesn't happen on a parameter of the function, it happens on this reconstructed variable that's local. So that's the AST transformation that we're talking about, that the compiler has to do for the offload kernel. So name changes, as I mentioned, we'll change the name. DPC++ today is using the typeinfo mangled name form. And if you demangle that, you get this typeinfo name for kernel name, which is really not that meaningful to anyone, or could be confusing, right? Nothing tells you this is an offload kernel or an entry point function. So instead, what we will do is we're using the naming scheme for a function template, a function named SIGL kernel caller, parameterized by the type of the kernel name. and just emitting that. We use the leading underscores so that we have a reserved name, so we won't conflict with anything the user writes. And then this will demangle with your favorite demangler, to something that identifies it as that entry point function, the SYCL kernel caller function. Today, DPC++ uses this built-in function named SYCL unique stable name to obtain a unique name for unnamed Lambda support. Since we are going forward with an approach that doesn't require us to do special things for to coordinate that naming across the host and device divide, we will no longer need this function. So we are planning to deprecate it and remove it. Or yeah, because it actually already exists upstream. It was pushed upstream as part of that initial 2020 or so effort, but never really used. The built-in functions for coordinating between the front end and the runtime library are listed here. I think these are up to date. I think we might have made some minor changes that I haven't reflected here in the slide, but doesn't change the overall plan. But the idea is the SYCL runtime library, given the type of a kernel name or a kernel name type, can call one of these built-in functions to get the data it needs. For param kind and such, that just lets us know if it's like a fundamental data type or if it's a one of those SYCL special types like a stream or accessor. Gives the param size and a bunch of different details.
What do you mean by kernel side?
I'm sorry, audio cut out there. Could you say that again, please?
Can you repeat the question?
Okay, I was curious about what is the kernel side.
Sorry, what is the?
Yes, what the kernel size is.
Oh, the kernel size. Thank you. That is the size of the kernel object itself. So going back a few slides where we had declared the kernel by the name of K with type kernel, the size of that object. And that today I believe we only use that to ensure that the size of the object that's generated on the host compiler matches the size that is generated on the device compiler. If those don't match, right, then we're going to be in an undefined behavior scenario where the representation of the kernel object is not the same on the host and device. And that means the data members and such don't line up. I actually don't think we're going to need this built-in function for the new design. But since the SYCL runtime currently expects it, we may have to provide it. But maybe we won't end up needing it.
Tom, quick time check. We are 5 minutes to the end. Do you have many slides?
Okay, great. Nope, I think we're down to like the last one or two.
Good.
So in going through this effort, we have identified a number of concerns with the SYCL specification where things are not clear, or where we don't know exactly how certain things are supposed to work. So we've been opening up SYCL specification issues. None of them have been resolved yet, but part of the process. And then our upstream status, like I said, we've had 3 PRs land, so we have the AST support in there that you can play with via Compiler Explorer. We will soon, hopefully this week yet, have our first PR submitted for the initial code generation. But that's still going to be pretty limited because we're still going to be missing support for decomposing kernel objects where we have to, and SYCL special types, we don't have support for those yet. There's documentation for the SYCL kernel entry point attribute upstream, and I can pull that up briefly if we want to. We are trying to ensure that we are providing support for SPIR-V, CUDA, or NVPTX, AMD GCN all upfront, so that we are not viewed as having any particular favoritism towards SPIR-V. We want to make sure everything's working for all of the different backends. Built-in functions are underway. Hopefully we'll get a PR up for those in the next maybe 3 weeks or so. Hopefully in the next 3 weeks, because the person working on those will be going on maternity leave around or shortly after then. We've started on work to make sure that we diagnose kernel name types that have portability limitations or that are not valid. And then we need to work on kernel argument decomposition, support for special types, some address space concerns with how the kernel object is handled on the device side, other diagnostics. So we have a lot of work ahead of us yet. And that's it.
Thank you, Tom. Any final questions or any comments from anyone on the call?
I have maybe a bit off-topic question, so sorry if that's the case. But AMD is currently working on adding SPIR-V support to their ROCm runtime. So does it make sense to work on adding AMD GCN support here?
I would think so, because I mean their runtime is HIP based, right, or HIP CUDA kind of interface, and we certainly would like to have our customers using SYCL, and if they want to target AMD.
But
fine.
if AMD will be able to ingest SPIR-V soon.
Yeah, but maybe we get a benefit from going directly from SYCL to.
Okay.
I don't know.
I mean, the AMD GPU works directly today.
Yeah.
No need to wait for SPIR-V working in ROCm.
Yeah, there's no benefit today. I guess in the future, if they switch to SPIR-V and they really commit to that, then that might be something we can evaluate from the perspective. Also, it's something maybe the community wants, right? Any other questions or comments before we wrap it off? I have a short question. Do you have a sense of the timelines to get more of the SQL run? Well, SQL frontend in particular upstream. Is that like months, couple of months, years?
Definitely months. Our current goal is to pass the SYCL conformance test suite around the June timeframe. I'm somewhat skeptical that we're going to hit that target, but we will. Now that we've getting kind of the base infrastructure in place, I hope we'll be able to make faster progress, because we'll be doing more incremental work and less design heavy work. So hopefully we'll get some acceleration there.
Yeah.
And then the SYCL runtime is going to have to be pushed upstream, and of course they're blocked somewhat on us getting things in place, and we're still discussing some of the design aspects of how that SYCL runtime will be submitted upstream to begin with, and what it will look like, and all of that.
Yeah. Okay. We can follow up with that in another session or offline as well. So yeah, really glad to see the efforts of the SYCL live streaming happening there. Once it is up there in LLVM, the community can also decide what other things they want to do with it, right? Maybe they do want to do other backends or other things there. So thank you everyone for joining. Thank you very much, Tom, for presenting today. And remember, we have a Slack and an email alias and an email list, so feel free to engage there. And thank you everyone for being here today. Cheers. Bye.
Thank you.
Thank you. Bye.